Welcome and hello. In this video, our group will present about forest loss and vegetation assessment using Google Earth Engine, GEE and ArcGIS. Now, let me introduce my group members.
Now, I will briefly introduce cloud computing and explain its role in natural resources monitoring. Cloud computing allows users to store, process, and analyze large volumes of environmental data through the internet. Unlike traditional methods that rely on powerful local computers, cloud computing provides high computing power and storage online, making data analysis faster and more efficient. This is especially important in environmental study where large satellite datasets are involved. One well-known cloud-based platform is Google Earth Engine or GEE. Google Earth Engine provides access to a vast collection of satellite imagery such as Landsat, Sentinel, and MODIS. Users can analyze this dataset directly in the cloud using programming language like JavaScript or Python, without the need to download the data. In natural resources monitoring, cloud computing and Google Earth Engine are widely used to study forests, agriculture, water resources, and land use change. This technology supports large-scale, near real-time analysis and help decision makers manage natural resources more efficiently and sustainably.
Now, I will walk you through the technical demonstration of our project. The purpose of this task was demonstrate the power of cloud computing of environmental monitoring. Specifically, we use Google Earth Engine, GEE, to efficiently detect and analyze forest loss over the chosen area. Instead of downloading terabytes of satellite data to our local computers, a process that could take weeks, we access and process it directly in the cloud in a matter of minutes. This allows us to focus on analysis rather than data management. Our group chose 4 distinct locations to highlight different deforestation drivers and ecosystem. First place that we choose is Miyazaki, Japan, a temperate region where forest change may be influenced by urbanization, typhoons, or sustainable management. Second place is Kalimantan Tengah, Indonesia, a tropical rainforest hotspot experiencing significant deforestation due to palm oil and logging. Third is Nairobi, Kenya, an area showing urban expansion and its impact on surrounding woodland and agricultural frontiers. And the last place that we choose is Dios de Madre, likely a region with unique ecological value, possible facing pressures from agriculture and development. For our project, we did not rely on just one tool. We used a 2-step workflow that leveraged the unique strength of 2 powerful platforms, which is Google Earth Engine and ArcGIS, specifically ArcMap. Let me explain why we use both and how they fit together. First, Google Earth Engine or GEE. Think of GEE as cloud supercomputer and geospatial data. It's a web-based platform where you can instantly access petabytes of satellite imagery like the Hansen forest change data we use, without downloading anything. Its biggest strength is processing power. Using Google server, it can analyze decades of data for entire regions in seconds or minutes. We use GEE for exactly that, to quickly process, analyze and detect forest loss across all 4 of our global locations. Then, we move to ArcGIS, specifically ArcMap. Think of ArcMap as the professional cartography and precision GIS studio. It's a desktop software installed on our computer, renowned for creating publication quality maps and performing detailed spatial analysis. Its strengths are in map design, layout, and advanced geographic editing, in where we make our map clear, beautiful, and ready for presentation. We use ArcMap to take the result from GEE, refine the visual, and combine everyone maps into our final group layout. So, to compare them directly, GEE is for large-scale cloud-based analysis. It's about speed and scale. ArcMap is for desktop-based cartography and detailed GIS work. It's about precision and polish. This key is these tools are not competitors. They are collaborators. The key is these tools are not competitors. They are collaborators. Here was our integrated workflow. Step 1, analysis in GEE. We use it as our data mining and processing engine in the cloud. Step 2, export. We send the finished analysis our forest loss maps to Google Drive. Step 3, cartography in ArcMap. We imported those maps to design, label, and finalize them for this presentation. This approach gave us the best of both worlds. The unmatched analytical scale of the cloud and the polished, professional outputs of desktop GIS. It's a powerful combination for modern environmental monitoring. Now, let's look how we produce our map and look at the result this workflow produces.
And now for the methodology of the forest loss and vegetation assessment using Google Earth Engine and ArcGIS. First, we need to insert the text, which is the code that we obtain based on our area of interest in our Google Earth Engine, GEE. Using the Google Earth Engine, we can generate the map that we needed. Open the GEE and run the GEE with we run the forest loss in the GEE. And then the GEE will run our code and generate, and our map will be available. Download the map, and the map will automatically transfer into our Google Drive database. With that, we will have the map automatically for ourselves. Next, using the ArcGIS software, we will be inserting the forest loss file and the shape file of our area of interest. From this ArcGIS, we will be constructing the properly show data on the map. We also need to download the GADM data from reliable sources. For my map, I obtained the data from simplemap.com. It can provide us with various GADM data across the world. Then we insert the GADM data. Next, we need to select the AOI area of interest, then the area of interest will be extracted by mass. Lastly, we will change the color of the map to properly and visually show the forest loss on the map.
There are 4 maps in the result, which show the spatial distribution of forest loss across 4 regions. Start with Central Kalimantan, Indonesia, Nairobi, Kenya, Miyazaki, Japan, and Madre de Dios, Peru. The yellow areas represents regional boundaries, while red points indicate location of forest loss events. Differences in density and clustering reflect varying levels of deforestation pressure and land use drivers. Central Kalimantan shows widespread and dense forest loss across the region. The distribution of red point is extensive, indicating large-scale and continuous deforestation rather than isolated events. This pattern is strongly linked to oil palm plantation expansion, logging activities, both legal and illegal, peatland drainage, and fires, which accelerate forest degradation. Overall, forest loss in central Kalimantan is high, spatially extensive, and human-driven. Map 2, Nairobi, Kenya. Nairobi, Kenya displays very limited and scattered forest loss. Red points are sparse and mainly concentrate near urban edge and infrastructure corridors. This reflects Nairobi's status as a highly urbanized region, limited remaining forest cover, and forest loss is driven mainly by urban expansion rather than agriculture deforestation. Compared to other regions, overall forest loss in Nairobi, Kenya is low. Map 3, Miyazaki, Japan. Miyazaki shows a moderate but evenly distributed pattern of forest loss. The red points are widespread but not highly clustered, suggesting controlled and managed forest use. Key drivers include commercial forest and timber harvesting, forest rotation practices, and strong forest governance and regulation. As a result, forest loss occurs regularly but remains regulated and relatively sustainable. Map 4, Madre de Dios, Peru. Madre de Dios, Peru exhibits very dense forest loss with strong spatial clustering, particularly in southern part of the region. This area is known for artisanal and illegal gold mining, road expansions, especially along the interoceanic highway, and weed enforcement in forest areas. The concentrate hotspot indicate intense and accelerating deforestation pressure, especially along access routes. By comparing all the map, we can know deforestation ranking. Start with highest to the lowest one. Based on the spatial density and clustering of forest loss, Madre de Dios, Peru is the highest forest loss, driven by illegal gold mining, road access, and weed enforcement. Second highest is Central Kalimantan, Indonesia, large-scale agriculture expansions, logging, and peatland fires. The second lowest is Miyazaki, Japan, managed forestry with harvesting balanced by replanting. And the lowest one is Nairobi, Kenya, urbanized region with limited forest remaining. And that's all for the result part. Thank you for your attention.
In conclusion, cloud computing enables efficient storage, processing, and analysis of large environmental dataset without the need for high-performance local computer. Platforms such as Google Earth Engine provide easy access to a wide range of satellite imagery and cloud-based analytical tools for geospatial analysis. By supporting large-scale and near real-time monitoring of forests, agriculture, water resources, and land use change, this technology enhances decision-making and plays an important role in promoting sustainable natural resources management.